Let's talk about factoring the polynomials in the context of partial fractions. What does it mean? And we know the basics of factoring based on our high school maths that we have done, but it never hurts to do a quick refresher because factoring polynomials is going to be the most important step, at least in the or the first initial important step whenever we try to resolve a rational expression into partial fractions, and hence let's do a quick refresher. So on the left, if you see, I have put some of the useful identities that we frequently use when we factorize. And whenever we say factorize, basically what it means is breaking it into simpler factors. Whatever given expression is that. For example, let's say we have a square minus b square. When we say factorize that, basically we check whether it can be broken down into a simpler expression like this, where we say a plus b into a minus b. That's what we do here, okay? And over here, sometimes the factors are on the each side, but you can understand wherever you have the simpler factors, that means they are factorized. And when you move from the simpler factors to a complicated equation, that's called as defactorization. So that's what the concept is. So if you see here, we are taking down a slightly combined complex term and breaking it down into factorizing into two linear factors, and so on and so forth. And typically, if you see in the context of partial fractions, I think the first three or four formulas are only important over here up to this, I would say. Mainly the first three, others are just for reference. And if you see on the right side, we have put some examples. For example, let's say if this was given to you as the input polynomial, which is quadratic in nature, the first check that we do is, can that be factorized? Okay, and if yes, how do we do that? Then we do it in this fashion where we say x plus 3 into x plus 1, and if you kind of multiply and open these brackets, you'll get this equation. And we have seen in the good old days how to factorize. We have to take this number and then we have to take this number. Whatever two numbers we pick up, those should be, when those two numbers are multiplied, for example, we are picking up 3 and 1 here. When these two numbers are multiplied, the multiplication should match the last constant term, and the net addition or subtraction of these two terms should match the middle term. So this 3 plus 1 is 4 and 3 into 1 is 3. That's what it is. So that's how we factorize. So in this case, this equation is factorized into these two simpler equations, and each of this particular expression or sub expressions are called as factor or factors. Similarly over here, not in every case that you will get a quadratic equation. Sometimes it might be a plain vanilla linear equation. For example, on the left hand side, if you see, we have got 2y plus 6. And how can we factorize? We know that we can remove 2 as the common. So we remove 2 as the common, and in the bracket we put y plus 3, and that's how we factorize in this case. Whatever is the given equation, can we break it down into a simpler format to any extent, or however we can? Is that possible? And if it's possible, then breaking it down is nothing but factorizing the polynomial. In this case, we have 3y squared plus 12y, and if you take 3 and y both common, because the y is repeating, then you get 3y in the brackets y plus 4. Similarly over here, if you see, this kind of fits into this equation where we have something called as a square minus b square, where a is, you can consider a as 2x and b as 3, and when you expand it, then you get 4x square minus 9. But if you kind of factorize it using this identity a plus b and a minus b, which will be frequently used in factorizing polynomials in the context of partial fractions, so you better remember this piece over here. So when you kind of factorize that, then you get a plus b and a minus b, which is 2x plus 3 and 2x minus 3. So that's one of the important steps of factoring polynomials, and whatever I said till now was a quick refresher and the important identities in case you have forgotten from your earlier school maths what you had done. So there's a quick refresher. Now let's get back to how do we kind of use this, and what is the initial housekeeping steps that we need to do before we actually start solving the problems. In today's episode, we'll not actually solve a problem, but we'll do the basic checks and balances before we start solving a rational expression into a partial fraction. And as always, in the previous video, we discussed this, where the very first thing that we will do is to check if the rational expression, which is something of this sort, I've given you a few examples, which is nothing but a ratio of two polynomials. We need to check if the rational expression given is a proper fraction or an improper fraction. And if you recall from our last episode, we discussed exclusively on this one where we check the degree of the numerator and compare with the denominator and decide if it's proper or not. If the degree is less, if the degree on the top is less than the degree of the bottom, then it's a proper fraction. Whereas if the degree on the top is greater than or equal to then the degree at the bottom, then it's an improper fraction. So the first thing that we always do is the same check. And if you see here, I put down some rational expressions of polynomials, and we'll be using that through rest of this episode. So if you see here, what are the different expressions? Let's quickly go through whether it's partial or impartial. Okay. So if you see here, and for each of this, let's say the numerator is this and the denominator is this, and we have to just see whether it's greater than or greater than equal to or less than. We have to just check this, okay, and let's solve that. So if you see here, what is the equation in the numerator? It's x to the power 1. So it's 1 here, and the bottom is quadratic equation of degree 2, and we have 2 here. So 1 is less than 2. So this is going to be a proper fraction, okay. Similarly, if you see here, what is the degree in the numerator? The degree in the numerator is 2. And the degree in the denominator, if you take this as to the power of 1 and if you multiply this, the exponents get added. So 1 plus 2 becomes 3. So the degree in the denominator is 3. And again, 2 is less than 3. And hence this is a proper fraction. If you check out this, the degree in the numerator is x to the power 1. We take 1 here. And what is in the denominator? We have the power of 1 here and multiplied. If you multiply this over here, when you open the brackets, the degree of this variable is 2. So when you multiply this, this is going to be a cubic function. So we are going to get the degree as 3. And obviously 1 is less than 3. And again, by our thumb rule, this is going to be a partial fraction. Then if you come down here, and if you check out the numerator again, the degree is 1. We're going to put 1. And the degree in the denominator is again x to the power 1 here. And we have 2. So when we add that, once we multiply this, the exponents are going to get added. So 1 plus 2 is 3. Again, it's going to be cubic function. And 1 is less than 3. Again, this is going to be a partial fraction. Same way here, the degree to the power of x is 1. And the degree to the factors in the denominator is going to be 3 again. We have x to the power 1 and then 2 here. When we add that, it's going to be 3. And again, 1 is less than 3. We are going to call this as a proper fraction. Okay. And if you see the last example, which is going to be the exception, the degree in the numerator is 4. The degree in the denominator is 3. And 4 is greater than 3. And hence, this is going to be a improper fraction. Okay, this is the only exception where this is going to be improper fraction. Okay, so that's how we see that. That's the first check that you'll always do in case of any problem that is related to partial fraction. Always check if the fraction is proper or improper fraction. And for this rest of this episode and maybe next few episodes, we will not be focusing on improper fraction. We'll be talking that separately in a different episode because the calculations to do that are different. So whatever I'm going to talk going forward, at least in this video and the next two videos, will be strictly applicable to all the partial fractions. And I'm going to take the same examples that I mentioned here. And that's the reason I kind of took a couple of minutes to explain whether it's partial or impartial. And these are like important expressions. It's a good assortment of different expressions and we can play around that one. So except for the last expression, which is improper fraction, we're going to focus on the rest because the rules of whatever I'm going to tell now applies to only proper fractions. So keep the improper fraction aside for the minute till we come back to solving proper fractions separately in a different video much further down on this series. Okay, after you check the first step, whether the fraction is proper and improper fraction, let's assume that all our fractions are going to be proper fractions, which is what we have done here. Let's assume that we have all of this coming together. All the expression that we have is only proper fraction over here. Okay, and let's focus on that, what it means. Okay, the next step is, we just saw what is factoring polynomials means. The next step is, we need to take each of the proper fraction. And check if the polynomial specifically in the denominator can be factorized. Is it possible? If and when. Sometimes it's possible, sometimes it's not possible. So wherever it's possible, we need to break it down to the lowest level, like how we discussed over here in this example. Break it down as much as possible, either using these useful identities or some of the straightforward examples. just just factorize the given polynomial into simpler terms as much as possible. And what are some of the examples? I'm taking the same example that I mentioned here. Some of the examples I've picked up and put it here. Okay, so let's say we have got three examples. So if you take the first example, the numerator cannot be factorized, and mostly we'll be talking about factorizing denominator because numerator might be sometimes simpler and it's already factorized. But let's focus on the denominator. We have x square minus 2x minus 3, and this is the given equation is quadratic in nature in the denominator. But yes, can it be factorized? Definitely yes. If you do this way, x minus 3 and x plus 1, if you do it this way, we break down this quadratic equation of degree 2 into two simpler linear factors of degree 1 each. So, and this is the simplest form that we can get. We cannot get any simpler than that. So yes, in this case, the given equation, at least the denominator can be factorized, because if you kind of multiply this bracket, you'll get back this equation. And like I said, the way you do is, let's say you have x square minus 2x minus 3 as the equation. You need to pick up two terms. In this case, this minus 3 and plus 1, which when you multiply will give you this term, which when you add subtract minus 3 plus 1 will give you minus 2, the middle term. And if you can find those two terms, that means the given quadratic equation can be factorized, and these are the factors. So in this case, yes, this can be factorized. The first equation can be factorized. Let's talk about the second one. Second one, where we have x square plus 1 in the numerator. Again, this is quadratic and we cannot factorize that. But like I said, most of the times it's the denominator that you need to focus. So let's focus on the denominator. If you see the denominator over here, we have got two factors, x, and then we have x square minus 1 within the bracket. And this you can equate to a square minus b square, which is what I told, that this equation will frequently come, or this identity might be frequently coming here. So we can do this where we can factorize into two simple factors, which is a plus b and a minus b. So we can take that, and this is how it's factorized. If you're taking the x square minus 1 is equal to x plus 1 and x minus 1. That's what we have it over here. So again, in this case, we had an equation which appeared to be quadratic, and we were able to factorize. And if you see now, there are three factors, and we cannot go any simpler than that. And all the three factors are linear because each factor's degree is 1, 1, 1, and that's what is linear all about. Again, let's take one more example over here. In the numerator is already factorized, we cannot do anything about it. But in the denominator, again, if you see the same term, x square minus 1, and applying the same rule, which is a square minus b square, we can factorize it. So these two terms can be broken down into these three terms over here, and we have seen that that's how we can factorize it. Hold this for now, we'll come to this when we solve the problem, so don't worry about this for the time being. In fact, I might just remove it from here to avoid the confusion. Okay, so if you see, again, we have taken the denominator and we have tried to factorize it, and we have got three linear factors which has the degree of 1, 1, and 1, because that's what linear means. Over here you had one linear and one quadratic, and since we could factorize the quadratic, we could get three linear terms, because the quadratic itself broke into two linear terms, and we had this original linear term from here. So yes, so the step 2 is factorize if and wherever possible to the lowest degree, all the way to the linear expression if possible. Yes, we have tried that in some cases and it has worked, and we know how to factorize. And like I said, we are not going to discuss improper fractions, so we're going to remove this because that is going to be done separately. All the things that I'm talking now, starting from this step and going forward, is going to be applicable only for proper fractions. Okay, now that's step number 2. So what is step number 1? We check whether it's a proper or improper fraction. Step 2, we try to see if it can be factorized, and if yes, we have factorized it. And step 3 is sometimes the given expression cannot be factorized. It's not possible. For example, there could be some quadratic equations. Although we had quadratic here, but this quadratic were factors, or we were able to factorize this quadratic. In certain instances, which we'll see here, the two examples, we will see certain times that we cannot factorize the given equation, so we have to keep it as it is. For example, if you see here, in this case, we have a quadratic equation here, and there is no way we can factorize that into a simpler term. It does not fit into any of the category, or we cannot apply any of the useful identities over here to factorize that. So in that case, we have to leave it as it is. We should not touch it, and then we'll solve it differently. Similarly, at the bottom over here, in the previous cases, we had x square minus 1, and hence we could apply the a square minus b square identity. But over here it's x square plus 1, and there is no identity which says a square plus b square. We don't have anything to solve that, and hence this quadratic will be left as quadratic, and we cannot factorize. We still do have one linear here and one linear here, but the other factor is quadratic in both the equations or both the expressions, and that cannot be factorized. And hence what we do is we do not do anything, we just leave it as it is. So it cannot be factorized, we leave it as it is, no change. So those are three simple steps that we apply before we really start solving or breaking down a polynomial or decomposing a polynomial into a partial fraction. Those three steps are: check for proper or improper fraction; step 2, factorize if possible using the identities that you already know; and step number 3 is if factorization is not possible, then do not worry, just keep it as it is. There will be different steps to solve this problem. So that's what I wanted to bring into this episode of why factorizing is important and how should we think about that in the context of partial fractions. And then we will see how to apply this in actually solving some of the different types of partial fractions.